Okay, hello. This is our short lecture on coordinate systems and changes to them. And we'll begin with waiting for this thing to get its focus back. And the delay also should improve as we get that down. Okay, so just stick something here to hold the focus. So we have coordinate systems. We think things of x, y, z, or we may want to have x prime, y prime, z prime. And you want to be able to go between these. You may even go to things like, say, r theta phi, spherical, or polar coordinates, sometimes called rho theta c, some such thing. Now, how do you go between these? Let's first talk about rotations. And rotation, of course, might have x. Well, we want it to be right-hand coordinate system, so if we make y go away from us, then x cross y is z. And we may want to rotate it so maybe x prime is up here and y prime is a little bit that way, and z prime is somewhere there. And so we don't know exactly what that's going to be. We have to specify it, of course. We're going to do equations. But typically, we'll say that we have x, y, z is a vector. It's equal to some rotation matrix times, oh, let's put the primes over here. X, y, z, right? And then what are some properties of this rotation matrix? So let's first write it down because we might as well. It's going to be an array of, in this case, 3 by 3. And what the elements are is the cosine of the angle between, see this one we're taking x and we're multiplying by this to get x prime. So it's cosine between x and x prime. Over here it's the cosine of the angle between x is going to be come in from that side and y prime. And down here it's the cosine of the angle between z prime and x. And then in our second position here, the second column, it's the cosine of the angle between, now instead of having x's, we're going to have y's. So x prime and y cosine angle y prime and y cosine of the angle z prime and y. And over here it's cosine of the angle between x, x. Yeah, this is the third column, so it's z. So it's x prime and z, cosine of the angle between y prime and z, cosine of the angle between c prime and z. And then we've got our x, y, z. So what the, sorry, I guess I got cut off here. So our R matrix here is the matrix of cosines, sometimes called direction cosines. And if you want to do a rotation, that's the way to do it. Now, oftentimes you might think of, well, I thought that they had cosine thetas and sine minus sine thetas and plus sine thetas. And remember, if an angle is equal to 90 degrees plus theta, then you bring a cosine into, let's say, plus or minus theta, into plus or minus sine. And so you get sines from these angles if they're shifted above 90. And so you expect that if, of course, z stayed where it was, then cosine z to z is just a 1, and these other angles are probably still going to be perpendicular. You want your x, y, and z axes to be perpendicular. And so these, by the way, these angles I'm talking about, they're the axes, old and new. So as I was saying, if x, y, and z prime are going to still be perpendicular to each other, then the angle in z stay the same. They get a 1 here. They're going to both be 0 because they're still all going to be 90 degrees. Cosine 90 degrees is 0. So then you're going to have maybe something up here that tells you about the rotation. Be 0, 0, 0, 0, 1. Z is not involved. Right? That's a typical case about a rotation about a single axis. But if you have generally, okay, that was what it was, that's what it is now, okay, you go and you calculate all these angles out. If you have vectors, you can do a dot product for that. If you don't, then you're going to have to do some geometry. Now, one other important thing is that due to the nature of this, what you find is that the structure makes R times R transpose equal to the identity or 1, 0, 0, 0, 1, 0, 0, 0, 1 matrix. And so R transpose is actually equal to R inverse. And that's kind of important. The other thing I'd like to say here is that we often talk about vectors. So we'll talk about x sub n, where n equals 1, 2, or 3 for x, y, and z. And if you think of it that way, you can write down that x sub n is equal to the sum, in this case up here, prime, is equal to the sum of r times n j x j, sum is j equals 1 to 3. And so that is a way of writing this in terms of simple coordinates. And then you can write, and you notice how the things here, the one towards that are the ones that adds. If we went to tensor notation, we'd have to have one higher, one lower. It would mess things up a lot. We're not going to do that here. This is not a lecture at that level. So that's sort of what I wanted to tell you about rotations, and to bring in the fact of what a multiplication looked like. There's one other thing is, suppose I want to rotate a vector. A. Then I do that by A prime is equal to, of course, my R matrix times A. How about a matrix? if I have a matrix that corresponds to some object, I want to rotate it. How do I do that? Well, the easiest thing is to say I have equation A is equal to some matrix M times B. And so if I multiply this by R on both sides, R times A is equal to R times M times B. And this, of course, is A prime. Now, I'm stuck over here. I don't have B prime. Right? So if I want a B prime, I really need to have an A in front of it. And if I have an A in front of it, I wreck my equation. I mean, not an A, I have an R in front of it. If I have an R in front of it, I wreck my equation until I realize I can always insert the identity matrix. And so this is equal to R M I being this times B, which is equal to R M R transpose R times B. And so I have A prime then equal to M prime B prime if M prime is equal to R M R transpose. And so if I want to convert a matrix, I have to use R twice, once for each dimension. If I convert a vector, I only need to use it once. And that keeps our vector equations working in both coordinate systems. I think you can be able to generalize this on your own. Now what I'd like to do next is talk about coordinate changes. And so with that, I'm going to try to keep my focus here as I flip our page. And the if we do coordinate changes, say to rectilinear x, y, z to polar, which is cylindrical in 3D, or to spherical. How do I go about those, and can I say something general about it? First, let's look at the spherical case as an example. And just takes just a second here as I bring it back. Okay. Oh my. This is the details one has to worry about when one goes to come on. I have to, this doesn't work. I'm going to pause it and make it work. And you can do it, focus. It likes to focus way up here. I don't know why. It doesn't seem like it would be the default. Normally it would make a default in optics class, which of course we're in, being focused at infinity, because that's usually where things are. It's very strange that it wants to make the default focusing up there. So I'm going to pause. Okay, here we are back with our focus. So the spherical case, we understand because we have x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, z is equal to r cosine phi, cosine theta. And we all know that this is related to the sphere, because if you go at your standard x, y, z, then the spherical coordinates go as a a radius, a theta hat, which just goes down this way. And there still have to have the phi. And if you want r theta phi, then my phi is going to go this way. And you notice a couple of things about this. One is the relative directions depend upon where you are. Because r is always pointing outwards. So over here it's that way, over here it's that way. That means it's not just simple rotation. It's a rotation depends on where we are. And so that is going to complicate matters. The other thing we notice is that the r has units of length, and theta and phi have no units. That is also going to cause a lot of complications. And what we're going to do today is figure out how to deal with these complications. Now, the first thing to talk about is volume elements. Now, just as an aside, you've all known about dot products. We talked about dot products on the last side, right? So I'll just make a little aside up in this corner. So last page, dot products project. And that's why we get cosine theta, cosine or whatever it is from the dot product. So what about a cross product? Areas and volumes. So if I take a vector A and a vector B, and I take A cross B, which is A, B sine theta, that's the angle between them. What is that equal to? That's equal to this area of that trapezoid that's defined by A and B. So when I'm thinking about volume elements, I really should be thinking about cross products. Now, in volume elements, they're usually called edge products. And I think of dx edge, dy edge, dz. Now they're all perpendicular. So the sine theta is equal to 1, all of them. But notice the following. Dx edge dx is equal to 0, right? Why? Because if I have, and also dx edge dy is equal to minus dy edge dx. These are properties of the cross product. So now, if I want to get a volume element, I can write down an edge project. So to get volume, use an edge product. And of course, this rule. And so for spherical, I can write down dx, which I'm going to need straight from the formula up there. I take a differential of that. Dx is equal to partial r sine theta cosine phi times partial r dr plus partial x partial, and then partial y partial, no, we want dx. The partial x partial theta d theta plus partial x partial phi d phi. Right? And then all those dependencies are in there, and I can write down what it is. It is sine theta cosine phi dr plus r cosine theta cosine phi d theta plus, let's see, minus r sine theta sine phi d phi. And the minus, of course, is because the derivative of cosine is minus the sine. Similarly, I can get d y is almost the same, sine theta sine phi dr plus r times cosine theta sine phi d theta plus r sine theta cosine phi d phi. And dz is equal to cosine theta dr minus r sine theta d theta. And there's nothing there. No dependence on phi. So I then write out dx edge dy edge dz equals 2, and we're going to drop drop the multiples since 0. That is to say, use this. Then what do you get? Well, you get r squared cosine squared theta cosine squared phi sine theta d theta d phi dr. And notice I'm taking off, I'm starting with, let's see, the sine, starting with the dr from down here, I think. So I have to take then a d theta and d phi from either this way or that way. So I'll take both of those first. This one's got a minus on it, r squared cosine squared theta, sine squared phi, sine of theta, d phi d theta dr. And then I'm going to add to that a minus r squared sine cubed theta cosine squared phi dr d phi d theta. And then I've got a one more term here, plus r squared sine cubed theta sine squared phi d phi dr d theta. Now, before I combine these, note that this thing right here, if I rotate it around by 1, is equal to dr d theta d phi. But for this one here, in order to get dr d theta d phi, I have to actually swap 2. So this is minus dr d theta d phi. This is also minus, and this one is a plus. So when I combine those two, I have to, if I'm going to write dr d theta d phi after all of them, I have to put this into a plus, I have to put this into a plus. So they're all actually added together. And I also pull out in the front an r squared sine theta, which is common to all of them. And I get a cosine squared theta, and I'll collect the terms that went with that. It's a sine squared phi plus cosine squared phi. And then I have to add on a sine squared theta, and I collected the terms that went with that. It is a cosine squared phi plus a sine squared phi. And I've made them all dr d theta d phi. Well, that's 1. That's 1. And those both 1. That's 1. And so this is equal to r squared sine theta dr d theta d phi. So this is a way that you can, using knowledge that you already have, that is to say, edge products, like cross products, you can just take the original formulas that you had up here for your x, y, and z, take differentials, turn the crank, find lots of things that are equal to 1, get a simple formula, and this is equal to the spherical volume element. Now there's some other things you're going to need besides the spherical volume on. By the way, you can do this for areas as well with the very same technique. It's a little time consuming, but it really gets you this idea of what does a cross product mean. Dot product is projection. Then I probably should say that. Yeah, they project. It's projection. It's dot. Then a cross product is area. And that's sort of how you get the idea of Stokes' theorem as well, is through that idea. What I'd also like to do, though, in this lecture is to talk about all the other things you need. For example, what are the unit vectors in spherical coordinates compared to in Cartesian XYZ coordinates? What does the gradient look like? What does the divergence look like? What does the curl look like? And that's when these ideas I pointed up here about, some things you have to worry about, they really start coming into play. So let's just begin this but now let's find all the other things we need. Okay, so for example, the other things I'm talking about dl, which is equal to dx x hat plus dy y hat plus dz z hat. And I'm talking about the gradient, the divergence, the curl, and the Laplacian. Those are the things that we're after. And to begin with, let's think about what happens if we take a vector a n. And this is formed from something that looks a lot like this, except we're going to take a partial with respect to an. So it's partial xn plus, and you can think of the n's, remember, as sort of being x, y, and z, or r theta phi, or rho phi z, or whatever you want to take for your coordinates. Y hat partial y partial xn plus z hat partial z partial xn. And what this is going to turn out to be is hn times en hat, which means it's in the direction of the unit vector n, but it's scaled. And the scale here, they contain, so these units are all the same. The point is that these things all have the right units, whereas this I guess the scale here takes care of units. So the best way to put it. You can't add things that don't have the same units, and so the vectors, as they were unit vectors, they have unit length, but dr is r, right? So it's now dr hat, I suppose. Normalize out the length. All the lengths aren't the same, so these hn have units. And that's relative to this point 2 up here. They actually have units. So those hns are going to be pretty important in our work. And so if we were to write down just a couple of cases here, we find that a sub r, for example, is equal to, I'm going to write it as ex sine theta cosine phi, and ey, I'm going to put a vector sign in that because it's not unit. Ey has a sine theta sine phi. Notice I've switched from x hat, y hat, z hat to ex hat, ey hat to sort of keep this new notation so I can write them all like this, which is subscripts. And ez hat has a cosine theta. And this thing here turns out to be equal to, it has the same units as x or y or z, so it's simply er hat. The next one here, which is e theta, is actually going to be equal to r times e theta hat. I mean, this can't have any units, right, the theta hat. And so we're going to, neither does that. Well, this has units of length, so we're going to pull that out. Ex hat r cosine theta sine phi. It's interesting, the cosine sines don't have units. So there actually is unitless up here the way it's supposed to be, but this guy has units because of the derivatives and not taking away the r derivatives. So this dd, the x, y, and z here, we're left with units when we're all said and done. And so that's why we've got to pull them out, and that's this h coming out here. So we have HR is equal to 1, H theta is equal to R. Okay, so yes, so theta, cosine theta, it should be cosine theta cosine B. Sorry about that. Plus EY R cosine theta sine phi. Minus R, I guess it should be Z hat R sine theta. And over here, we've got R sine theta E phi hat. So H phi R sine theta. R sine theta E phi hat is equal to A phi. It's a vector, which is EX hat times minus R sine theta sine phi plus EY hat R sine theta sine phi sine theta cosine phi. And it has nothing from Z hat. Of course, you can also use the, sorry, nobody told me. Can also go the other way. You have R is equal to the square root of X squared plus Y squared plus C squared. Theta is equal to the arctan of the square root of X squared plus Y squared divided by Z. And phi is equal to the arctan of Y or X. If you're actually going to go the other way, you might need the derivative with respect to C of the arctan C is equal to 1 over 1 plus C squared. And from that, you can sort of go through and get EX, EY, and EZ from the other factors. Now, the first thing to note here, so we will find the H sub n useful for making units work. And other things. For example, the volume element. Is equal to H1, H2, H3 times dx1, dx2, dx3. And so if we look that out, Cartesian, H1 equals H2 equals H3 equals 1, and then the volume element is equal to 1 times dx, dy, dz. Spherical, we have HR equal 1, H theta equal R, H phi equal R sine theta. And so the volume element is equal to R squared sine theta, dr, d theta, d phi, which is what we had before, right? This is perhaps a little easier than going through all that math. And that already tells us one way in which these things can make it a little bit easier. So let's continue with that. And let's look at these quantities, right? We wanted DL. DL turns out to equal the sum of a sub n dxn, which we now know is the sum of e hat sub n. That's the unit vector with no dimensions. Now, of course, the problem is that, right, this may or may not have them. This does. And so the quantities, we already know what this is. We know that an is equal to hn times en, right? We derived that. And this is dxn. So again, these are fixing the dimensions. In the h, for the spherical case, hr was 1, okay, because that has r. dr is length, works. For d theta, d phi, this doesn't have any units, but those had either r or r sine theta. They had our dimension to give us lengths. So the h is patching up dimensions. That's how you're seeing that coming in. Okay, so that's dl. Now we need to look at the gradient. So gradient of u. We'd like to have we like to think this is sort of, if to get the units right, think du dl, right? We have dl up here, and that gives us a good idea of where to put the h's to fix the units, right? We got to put them in front of the dxn, and so the gradient of u is going to be the sum en hat unitless 1 over hn partial u partial xn. So again, all the terms of this have to have the same units. The hn fixes up the units. So again, once you know your hn, which you get from those derivatives, once you know the formula that converts one to another, which of course is needed before you can do anything anyway, right? Then that's got to come into play. Okay, the next thing we needed is the gradient. By the way, there's another way to think about this, and it's kind of an odd way, but the equals sum of the hn en, which is the an, of course, 1 over n squared times partial xn. And this is sort of the tensor way to think about it. Which is to have different types of vectors you have covariant, contravariant. You can't multiply two contravariants or two covariants. You have to have one of each. The hn squared converts between the types of vectors. And you can only multiply one type by the other. So you have to convert sometimes, that's what this does. And then you have these sort of intermediate things as the physical quantity, including the units on them, right? So that's a way to think about where some of these relations come from. They actually wanted to derive them. Then you use those tensor methods approaches, and you're going to end up sort of doing conversions like this. That's the easier way to do it. So the approach for the divergence then again, we're thinking about we need to correct the volume element size because it varies with where you are. And so we'll do that. And then we'll take the derivative. And then we'll put it back. That's our reason for writing the divergence this way. And so the del dot v is going to be equal to 1 over h1, h2, h3. That's to put it back, times the sum partial x sub I, we're summing over I, of h1, h2, h3 over h sub I times v sub I. So we do that, that's here, take the derivative, and then we put it back. So that's what those are for. If you're wondering what this is here, that's getting the units right, sort of correcting for this. So this kind of corrects that to get the units right. And anyway, that's the formula you have, and if you plug that in, you will be able to get all the forms such as the spherical divergence formula is so this is for spherical. Just to give you an answer, you know what it is in Cartesian, when all the h's are 1, it kind of falls apart. You have the sum over x sub I dv dx sub I. In spherical, which we'll use more than cylindrical and optics, so I use that one. You end up with 1 over r squared partial r of r squared v sub r plus 1 over r sine theta partial theta of sine theta v theta. And then you've got the 1 over r sine theta again. And sorry, 1 over r sine theta partial v phi partial phi. And so if you went and plugged into this, where the xi are r theta and phi, you're dividing out one of the particular ones. As you're taking the derivative here, some stuff, of course, comes out and cancels. Like if you're taking r derivative, you can pull out the sine theta. That cancels the sine theta from h3 on the bottom, or h phi on the bottom. And you end up with this, which is rather simple. There's an r in both of these that comes out because you're not taking r derivative, and that knocks out one of the r's from the r squared. So that's how this works. If you look, all the units on those three terms are in fact the same and correct. Okay, so the way that you can justify this, by the way, is you can take del dot sort of vi ei is equal to del dot h1 h2 h3 over hi times vi times hi ei over h1 h2 h3. Okay, so those cancel those cancel that. You actually have exactly the same thing now written funny, but you can do the product rule now for this. And so you have hi ei over h1 h2 h3 dot the gradient of h1 h2 h3 over hi e sub I. This is this. The dot product just gives you the right term. H sub I over this is actually what we have. And then we have to add on, though, the other term in the cross, which is h1 h2 h3 over hi times vi del dot ei hi over h1 h2 h3. And all of these turn out to be 0. I won't prove it, but that's sort of the justification. You take something, you make it look complicated, you do a product rule, one of them is this, the other one is 0. And that's how you can justify this particular type of analysis. Okay, the next step is the Laplacian. And I do that next because del squared is equal to del dot grad. So del squared u is equal to del dot gradient of u. And this is like, so u is above with v sub I going into 1 over h sub I partial u partial x sub I. And if you do that, you get del squared u is equal to 1 over h1 h2 h3 times the sum of partial x sub I h1 h2 h3 over hi squared. So now, whichever one it is, you're going to have the other two divided by that one. Partial u, partial x. Right, so that is our, I guess I need to circle this one. And I need to circle this one. These are our main answers. And so this one easily falls from the other two. That's why we did the plus in next. And the final one to do is the curl. And del cross D is equal to 1 over H1, H2, H3 times the determinant of basically the A's, E1, H1, partial X1, H1, B1, and then we run the same thing for the 2's and the 3, H2, E hat 2, which again is A2, partial X2, H2, B2, and H3, E3 hat, partial X3, H3, E3. And remember here that order is important. Because we're taking derivatives. So it's this second, that third. So you're taking derivative of these two with respect to x2, then minus that and that third. And so you need to make sure you get these things in the right order when you're doing it that way, so that you are taking the derivatives of correct things when you're applying that. That's not always the case when you're doing the determinant, but when you get derivatives, you have to actually watch out for that. And you can write out what the curl is. It's a complicated mess. You might say, well, I would like to see something in front of those x's, and maybe not something up there. All the terms have to have the same units. What are these things doing down here with these? And these are, I'm not going to get into that, because if you really want to get this, you're best off going ahead and looking at the tensor arrays, or just use the formula. It'll give you the right answer. So that is about all I wanted to do with this lecture on how to shift coordinates and get all the things you need to get when you do that, and get them correctly. So this will be the end of this lecture.